Hey guys, welcome back to our next lesson in calculus. This is Mr. Bean, and today we're talking about asymptotes, which hopefully is going to be a nice, clean review for you. But we're going to get into some more advanced type problems. So let's remind ourselves, what in the world is a asymptote? Well, a vertical asymptote, if you want to sketch kind of a teeny little graph like what I've done, a vertical asymptote is a vertical line, and it's going to be up and down like this. It's some imaginary line that you don't really see, but it helps us get the shape of the graph because this graph will not cross a vertical asymptote. So it kind of bends down to negative infinity or it bends up to positive infinity, but it's not going to cross it. And a horizontal asymptote is just like it sounds. It is horizontal, but the horizontal asymptote, the graph might cross it, but really what it does is it enables us to understand the end behavior of a graph. So if you go way off to the left, this horizontal asymptote is what the graph will approach. And same with the right side. The graph's going to approach that. So if you want to try and remind yourself something about this is that the vertical asymptote, it forces the graph to go to positive or negative infinity, and it will not cross the graph. And a horizontal asymptote, it's possible that the graph does cross it, but it can cross, an infinite number of times back and forth, but it's all about the end behavior. So with that, let's look at vertical asymptotes first, and we'll talk about horizontal. So here's a question for you. True or false? If you have the function f of x equals blah, 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 blah. In other words, whenever I do something like this, it just means it doesn't matter what's on top. So just a bunch of blah, blah, blah stuff. And then on bottom, you have x minus some number a. If you have this situation, then there must be a vertical asymptote at x equals a. Is this true or false? So based on your past understanding of vertical asymptotes, true or false? The answer is false. The answer is false on this. And the reason is because just because you have x minus a, it's true. X cannot equal a for the domain, whatever that number is. If this is a 3, then x cannot equal 3. But it's possible that there is a factor of x minus a in top. You remember this? And if it factors and cancels, that's not a vertical asymptote. That's what's called a hole. So we'll get into holes and discontinuities in the next lesson. For today, we're focusing on vertical asymptotes, but I needed to remind you because they're connected here. Just because you see this on bottom does not mean that represents a vertical asymptote, because you have to double check to see if it canceled or not with the numerator. So let's do some examples. First up here, we're going to find all the vertical asymptotes of this thing. So for that function, in order to know the vertical asymptotes, we need to factor both the denominator and the numerator. So let's take this, see if it factors here. Set up our little unfoiling thing, our reverse distribute, which is factoring, and we get the x in front. I try to make these nice and easy. And honestly, the numbers are usually in an AP calculus class. Most of the time, the factoring numbers are going to be pretty small. Let's see, multiply to negative 8, add to 2. That is going to be a plus 4 and a minus 2. And then down here, how do we multiply to negative 12, add to 1? That's going to be another plus 4 and a minus 3. Okay, so now that we factored it, you can see that those things cancel, which we'll remind ourselves in the next lesson. This would represent a hole. So that means this is your vertical asymptote, or represents, that factor represents. So where is the vertical asymptote? Only at x equals 3. We have an imaginary line straight up and down at x equals 3. All right, now that we know that is our vertical asymptote, let's evaluate the limit as x approaches 3 from the left side. So in other words, on a number line, if I had a number line here, and as we approach the number 3, as we approach this, getting closer and closer to 3 from the left side, is this graph going to be going to positive infinity, kind of like we remember this one, to positive infinity, or to negative infinity? So how do you do that? Well, we could try plug in the number 0, plug in the number 1, plug in the number 2, and we'll see as we're approaching 3, where is it going? So 0 is really easy. If you plug in a 0, you get negative 8 over negative 12. Okay, so that, if plugging in a 0, we get a y value of positive 8/12, which we would reduce.
Plug in a 1. Oh, this is a headache. 1 plus 2 is 3, minus 8, negative 5, over, what's this one going to be? 1 plus 1 is 2, minus is negative 10, so that's going to become a 1/2. You can see what I'm doing here, I'm just trying to do this real quick in my head. Next one, plug in at 2, so we go 2 squared is 4, 4 plus 2 times 2 is another 4, 4 plus 4 is 8, 8 minus 8 is 0. Let's not make some mistakes in mental math here, 0. And then 2 squared is 4, plus 2 is 6, 6 minus 12 is going to be negative 6, but this really becomes a 0.
All right, so there we have our answers, what these are simplifying to. So we have 2/3, then we get to 1/2, which is smaller, then we get to 0, which is even smaller. So it looks like we're going smaller, smaller, smaller. So really what we want to do is you want to know really close to 3. If we could figure out what's 2.99 and you get really, really close and you plug that in, we'd receive a really big negative number if I plugged that number into a calculator. So what I'm trying to get you to understand is you don't have to have a graph if you just plug numbers in really close to 3. This one is going to become like a negative big number. Okay, really, really big right there. So this one is approaching negative infinity. All right, let's do this again real quick. The same concept if we're approaching 3 from the right.
So if we're approaching this number 3, that just means if I'm going, I would go 4 and 5. Let's just do those real quick. Let me pause it and figure those out.
Okay, there's the numbers I got. 5 is a 23/18. 4 would become a 2. And as we get closer and closer to 3, so in this case we would plug in, if we were using a calculator, 3.001 or something like that. 3.001. If we plug that number into the function, we get really, really close to 3, and you're going to discover it is a very big number. We're approaching infinity. So actually, the graph is the original graph I gave you at the beginning of the lesson. This is the graph of that function. So this is the idea of vertical asymptotes. If we need to find the limit, looking at the graph, real easy to understand what the limit is. But if you can't look at the graph, you can plug in a number that's really close, and that'll tell you if it's positive or negative infinity. But you got to factor first and see which one doesn't cancel to get the vertical asymptote. Let's do horizontal asymptotes now. That is end behavior. Or in other words, what does the graph do at the end, way off on the right side, way off on the left side? It doesn't really ever end, but we just kind of pretend if you go way off. All right, so what does the y value approach as the x value approaches negative infinity? And, important and right there, very, very important, and positive infinity. We have to look at both sides. Usually it's exactly the same thing, but sometimes it's different. So, does it approach a specific number, or is it just growing without bound, going up and up and up and up and up, or maybe it's going down and down and down and down on the left? So that's what we're talking about here, growing without bound, or is it approaching a specific number for a horizontal asymptote? So here's our basic rules. Now the problem with the rules is some of you like to memorize rules. That's not really a good idea. You just want to kind of understand the concept of what's happening with these functions. So I tried to give you these notes where it will help you with the concept. You think about this, hopefully this makes sense. If you have a denominator that grows faster, what that means is on the bottom, if you go towards infinity, this is going to become a super duper big number. Now the numerator is going to be big too. I mean, come on, we're going to infinity here, but it's just not going to be nearly as big as the super duper big number. So when you have something being divided by a big number, you get really close to 0. And the bigger this number is, the closer to 0 you get. So just remember, super big on the bottom means 0. That's what this fraction approaches. Okay? What if the numerator and denominator are growing equally fast? That means you have a big number that is growing equally as fast as another big number. That means it equals 1. This is an oversimplification, okay? I'll give you examples where it's not going to be exactly 1 because you might have coefficients in front. So maybe you have like a 2 here and a 3 here. If you have the coefficients, then the answer would be 2/3. But the main concept is if you didn't have coefficients, then the answer is just a 1. Okay, and then if the numerator grows faster than the denominator, so we got the big number up here on top, well, think about this. Really super duper big number on top, and we're going to divide by a number not quite as big. Well, that means you're going to have a really big number. And because this gets bigger and bigger and bigger, the farther closer to infinity you get, and so therefore the y value is also going to approach infinity. Okay, now that that's as clear as mud, let's go on to trying to understand how fast a function grows. If you don't know which one of these is growing faster, it's going to be really hard to do this assignment and go through the rest of the practice problems. So, grab a calculator, and you need to kind of play around with understanding for yourself what these numbers equal. So here's your function. When x equals 1, okay, that's easy. That's going to be a 1. And then plug in a 10. 10 squared is going to be 100. And then plug in 100 squared. If you don't know what that is, you can grab your calculator, and you just fill this out. If you get scientific notation, just use scientific notation on your answers here. And fill this chart out. And then you want to see which one is going the fastest. Which one grows the fastest? In other words, if you get out to here to infinity, which one will be the largest number? So you can have an idea which ones grows faster. Okay, so go ahead and pause now. And I'll have this whole chart filled out so you can see it in just a minute. But give yourself a chance to figure it out. And here's our magic numbers. What I've done here is I've highlighted from the column when x equals 1, which one of these is the largest. So 4 was the largest here. And then on this column, which one was the largest? X to the 10th was the largest one when x equals 10. What about when x equals 100? Oh, it jumps back here to 4 to the x. And then here's an error. That's kind of weird. Error. That's because your calculator cannot handle the numbers that are extremely big. It's like an overflow error. It just cannot handle it. So notice that it can handle these. It can handle a natural log. What it can't handle is exponential functions. When the x is up here in the exponent, it's growing too fast. So that should give you a hint right away. These are growing much faster than these. In fact, you could have x to the 1 million. Blah, 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 x to the really big number, and it's still not going to grow as fast as an exponential function when you get to infinity. It might be bigger at first, but not forever. So here's the ranking. 4 to the x would be the thing growing the largest. 1, 2, 3, 4, 5, 6, and then a logarithm would be growing the slowest, which makes sense because a logarithm graph kind of does something like that and starts to even out a little bit. Okay, so remember that. This is important for us to do these practice problems, that exponential functions will grow faster than these other things. So it says find the horizontal asymptote. So in other words, the end behavior. What y value does this approach as x gets really big? So remember, we're trying to figure out which one's growing faster, the denominator or the denominator or the numerator. So when you look at these things, you look at the term that affects it the most. So x squared is going to affect this more. It's going to grow faster. So you don't even worry about this plus 4. It's just like, blah, doesn't matter. And then down here, the 3x is the term that affects it the most because it's going to grow the fastest. So nothing else really matters. So these are the only things that matter. So x squared is growing faster than 3 to the x, 3 times x. So x squared grows faster. That means numerator is bigger on top than the denominator on bottom. Therefore, it is growing without bound. There is no horizontal asymptote for this one. Okay, that falls under, if we go back here, that falls under this one. The numerator is growing faster than the denominator, so it's approaching infinity. So when it says find the horizontal asymptote, there isn't one. Next one. So we're looking at only the terms that are growing the fastest. So this plus 4, blah, 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 doesn't mean anything to us. The minus 5, blah, blah, means nothing to us. This is the term that's affecting the numerator the most. And down here on bottom, so the x and the x mean they're growing at the same equal amount. X grows just as fast as this x. So this is our rule number, our second situation where you have that they're growing equally fast. So remember how it was a big number divided by a big number equals 1? Think about that. You have super duper big number on top. On bottom, you have the exact same super duper big number times 3. So what is that going to equal? The horizontal asymptote would be of this function, y equals 1/3. That's the horizontal asymptote. And then this one here, you have, again, we don't worry about the plus 4. Down here, we're not going to worry about the minus 5. Those things are just too small to affect anything else as you get out to infinity. So we have x on top and then an x squared on bottom. Which of these grows faster? Obviously, this one's growing faster on bottom. So when you have that situation, you have a super duper big number on bottom. It is approaching y equals 0. That is the horizontal asymptote. All right, now let's do a weird one. What is the horizontal asymptote of this thing? If you remember at the very beginning of this part, I had this, you focus on the word and, positive infinity, because I didn't do it on these problems. I didn't check both negative and positive infinity on these. And why not? Well, I probably should have kind of force you to, but really, if there's no horizontal asymptote here, so it doesn't matter to check either side. But this one, positive infinity and negative infinity. If it's positive over positive, the answer is positive. Negative over negative, the answer is also positive. So it didn't matter there. What about this one? This one, no matter if the number is positive or negative, it's not going to affect the fact that we're going to 0. 0 does not have a sign. It's not positive or negative. So on these examples, I did not need to check both the positive infinity and negative infinity. But this is an example where I will need to. So here's what happens. Remember how the plus 2 doesn't really matter compared to this thing. And the minus 1 doesn't really matter compared to the x. When we're approaching infinity, I mean, really, let's think about this. A billion minus 1 means nothing. The minus 1's like, doesn't really do much at all. All right, so now we have this situation. We have this square root of x squared over x, and that's the only thing we're really focused on. Well, that's just the same thing as, if we simplified that, that's like x over x. Well, that's like the number 1, right? I mean, if we're going to have infinity over infinity, that's just the number 1. So the horizontal asymptote for this example is y equals 1 if we're having infinity over infinity. But that's only the right side. What if we did negative infinity over negative infinity? You have to use the original. So we're going to go negative infinity squared. What happens when you get negative infinity squared and then you square root it? So just think a really big number. This becomes positive. You know, like if I did a negative billion, squared it, and then take the square root of it, you're going to have a positive billion. You follow what I'm saying here? Plug in a negative billion, square it, and square root it, you're going to be positive. And then down here, if I had a negative 1 billion, well, then what happens is you have a 1 over a negative 1 billion. So we have a different one on the left side. So there are 2 horizontal asymptotes for that original function. That's kind of crazy. And that's because of this squared and square rooting thing. So you have to be careful. If you're not sure, just always plug in a positive infinity and a negative infinity. So a really, really big positive number, really, really big negative number to kind of test it out until you get more familiar with how these rules work. Once you get good at it, it's really just looking at it and you'll know pretty quick. All right, getting closer to the end here. Let's evaluate these limits. So notice on each of these I have x approaching infinity, x approaching negative infinity, x approaching infinity, x approaching infinity. When you have a limit of x approaching infinity, that is exactly the same thing as these instructions. Find the horizontal asymptote. That is all this means. Well, limits approaching infinity mean what is the end behavior? Is there a horizontal asymptote, or is it going off forever up or off forever down? Okay, the reason I have pause here is because I'm going to do 7 and 9 for you. You'll pause, and then you're going to do 8 and 10 on your own. So we're going to take a look at, let's first just ignore the things we don't need to worry about. We only focus on the term that's growing the fastest in the numerator. So this plus x, this minus 2 means nothing to us. And down here, the minus 1 means nothing. So these are the only things you got to focus on. See how nice that is when you approach infinity? Just get rid of the things you don't need to worry about. So what we really have going on here is a square root of 4x squared over 3x. Let's go ahead and simplify that. That really means we have 2x over 3x. And as you approach infinity, you're going to have 2 times infinity over 3 times infinity. So that's basically just 2/3. So the answer to this is 2/3. And we don't have to check the negative side because this is going to positive infinity. It's not going to negative. So the answer is 2/3. All right, let's skip 8 because you're going to do that one on your own. Number 9. So we're approaching infinity. So what does that mean? Here for this example, we're going to have, let's just focus on this fraction right here. So that fraction of 1 over x, if you have 1 over infinity, so x is approaching infinity, this is going to get really, really, really close to 0. So in other words, we have negative 4e raised to the really, really, really close to 0. It's approaching 0. Well, what's e to the 0? That is negative 4 times 1. Anything raised to the 0 is 1. So the answer is negative 4. All right. Why don't you pause now? I'll give you just a minute or so here. Just pause the video and work number 8 and 10 out on your own, and I will have those answers appear. Okay, here's our answers. Number 8 was negative 2/3. Number 10 was 0. Now, why negative 2/3? Because even though this would approach 2/3, we have to remember, it's just like number 7, that you have to plug it into the original. And so if you had it into the original and you're approaching negative infinity, this one actually is going to be positive and the bottom is negative. Why? Because you're squaring negative infinity. And when you square it, you get a positive number. And you square root it, it's still positive. But on bottom, you'd have negative. Okay, I know that's a little confusing. You might need to listen to that again. And then over here, what happened here? Negative exponents mean it becomes the reciprocal. So it's going to be 1 over e. In other words, it's 5 times 1 over e to the x. All right, so 5 times 1 over e to the x is just this, 5 over e to the x. And then x is approaching infinity, so it's e to the infinity. Really, really big number on bottom. When you have a really big number on bottom divided by a small number on top, you get 0. All right, let's go on to trig function horizontal asymptotes. Sometimes you get these trig functions mixed into it. So sine of x, we're approaching negative infinity this time. So sine x is going to bounce in between. Remember, sine and cosine, when you plug numbers in, the answer is always going to be between, so they're going to be in between the numbers -1 and 1. That's the range of sine and cosine. It just kind of remember with the wave graphs, it bounces back and forth, back and forth. The bottom of it's -1, the top of it's 1, and the middle is 0. If you remember back to our trig stuff. So the top number here is always going to be fairly small, between -1 and 1. This number is going to get really, really big in the negative direction. So if you have a really big number on bottom, so big number on bottom, and then just a number on top that's in between -1 and 1, well, that's getting real close to 0. That's what's happening for this. Okay, so it's approaching 0. This one. So what's happening here? You have cosine, so let's rewrite this. We're going to have -3 cosine of, what does 1 over x approach? If x is approaching infinity, 1 over approaching infinity is going to be 0. So then you have -3 times cosine of 0. What's cosine of 0? Cosine of 0 is 1. So you really need to know your trig values. And then that answer is -3. And then this one, if we are approaching infinity of sine x, what happens? X is approaching infinity. Think about the graph. Maybe this will make sense. If you approach infinity, the graph keeps going and going and going up and down and up and down and up and down. It never stops going up and down. It doesn't approach one specific value. It just bounces back and forth, back and forth, back and forth, up and down. So that means that this one, the limit, does not exist. There's no limit for this one because it's not approaching a specific value. Okay, how about this one? Again, this is going to approach infinity. So it's going to be 5 times infinity. It's going to get really, really big. But cosine of x, you might want to say that means this is just approaching infinity. But cosine of x is doing this graph thing again where it's bouncing up and down. It's a wave. And as you approach infinity, it's not going to a specific value. So this one, again, does not exist. Okay, you've done well. This is the very last thing I need to talk about. And it doesn't really have anything to do with asymptotes, but we threw it into this lesson because it is part of our calculus curriculum, and we want to make sure we get this covered. And the good news is it's pretty easy. This explanation might seem a little confusing. Watch this twice if you get confused about this last part, because it's really not that hard. So let's do this. We got this thing called squeeze theorem. Sometimes it's sandwich theorem, pinching theorem. Different people call it different names, different books. We're trying to figure out g of x, a limit. Excuse me, the microphone might be too close. Let's move that. G of x is the limit we're going to be focused on, how to figure out the limit of this thing. And we don't know how to do it, so it's hard. So what we do is we find a function that's smaller than that and a function that's larger than that are easier to work with. And if this function in between them, this is looks a little weird, if you're approaching some number a and the answer to the limit for f is, the answer is L, and you do the exact same number for the one that's bigger and the answer is the same thing, L, then that means the one in between, the answer for this one has to be L. So in other words, you don't know this one, but you know the left and the right, and if they're the same thing, then the limit for the one in the middle has to be the answer to that too. Okay, that seems really weird and seems obvious, but let me show you an example of what I'm talking about. So we're going to have the limit as x approaches 0 of this function, x squared times cosine of 1 over x squared. The answer you can see here, the answer is going to be 0. This is the graph. Okay, so we're going to approach zero, approach x equals 0 from both sides. The y value, if we zoom in real close, it's going to be 0. Okay, but what if we don't have the graph? How do we do this? So let's start off with, here's how this works. Let's start off with something we know, and that is we know that cosine of 1 over x squared, we know that this thing has to be in between, watch this trick, we know that the cosine of anything has to be in between the numbers -1 and 1. Kind of like what I talked about earlier in the lesson. The sine and cosine graphs are always between -1 and 1, unless it has something that we're multiplying by. All right. So if that's true, we have this x squared in front. Let's go ahead and multiply this by x squared. So I'm going to have less than or equal to x squared, and then I have cosine of 1 over x squared, less than or equal to symbol. So if I multiply the middle by x squared, in order to keep this balanced, I have to multiply this by negative x squared. So or by x squared. So I have negative x squared, and on this side I have to multiply by x squared. Okay, so what you have now is you have this function x squared times cosine of 1 over x squared has to be in between negative x squared and positive x squared. Well, watch this. Let's graph this thing. Focus on the graph here. This is the graph of x squared. Whoops. And this is the graph of negative x squared. So what you can see from this picture is that this squeezes or pinches the graph. It's the sandwich theorem. It's sandwiched in between these two other graphs. So if we can figure out the limit of the two red functions, the left one and the right one, then we'll know the one in the middle at that point. So what you do is we're going to take the limit as x approaches 0 of negative x squared. And we're going to take the limit as x approaches 0 of positive x squared. So what's the answer to this one? Well, that's easy. It's 0. What's the answer to this one? That's easy. It's 0. Therefore, by use of the squeeze theorem or the sandwich theorem, if the one that's smaller and the one on bigger, if they're the same thing, 0, then the one that's in between them must also be 0. That's how we get our answer. That's the squeeze theorem. Okay, so you start off with the easy thing that you know. Usually these are going to be like some trig functions. Something that you know what you can do with that it's small, that's got to be in between two numbers, and then you start multiplying it over. All right, that is the end of this lesson. Rock that mastery check. See you back in the next lesson.